Southeast Asia. The fleet needed a weapon system precise enough to score hits on bridge and barge-sized targets. A precision first-pass kill capability was needed to keep the element of surprise and to improve aircraft survivability. The Naval Weapons Center responded by adapting existing Air Force laser-guided bomb kits to fill Navy and Marine needs. A lightweight handheld laser was quickly developed to designate targets for the adapted bombs. The laser-guided bombs followed the reflected laser energy to the designated target, improving bombing accuracy significantly. Medium and low energy lasers are very effective for target designation and for other military applications because the narrow, intense beam of coherent light is extremely concentrated in energy and travels over long distances. Also, laser devices are small and portable. Laser designators can pinpoint specific targets within a target complex. The second system adapted, also from Air Force assets, was PAVE Knife, a television targeting system with a laser target designator. In January 1973, using the adapted PAVE Knife system, Navy A-6 aircraft from Squadron VA-145 destroyed 16 bridges in North Vietnam. The mission was completed in under 3 hours, with no losses. Today, lasers are an integral part of naval warfare, used in target designation, ordnance guidance, ranging, weapons fusing, and communications. Laser use and sophistication continues to expand. The word laser is an acronym for light amplification by stimulated emission of radiation. The components of the basic laser are an energy pumping source, usually a gas-filled flash lamp, the lasing element, and 2 mirrors. The lasing element can be composed of crystals, such as ruby or gallium arsenide, or of gas, such as carbon dioxide or ammonia. As the flash lamp pulses, it pumps energy into ions in the lasing element. The energized ions emit particles of light, photons. These photons strike other ions, stimulating them to emit a second photon of the same frequency in phase with and moving in the same direction as the bombarding photons. Very quickly, a cascade of photons develops in a rapid chain reaction. The photons are reflected between the mirrors, amplifying the cascade to a very high level. Controlled electro-optically, the photons burst through the laser output mirror as a narrow beam of coherent light of high peak power. Depending on design, laser light is emitted either in pulses or in a steady stream. The precision of laser optics is extremely critical. A cumulative error of 100 millionth of an inch in optical surfaces can degrade the beam quality of a system significantly. Refinements in optical surfaces are measured in hundredths of a percent. Extensive research is being conducted to develop optics which best meet the cost and performance requirements of military laser systems. The most common military laser is the neodymium-doped yttrium aluminum garnet laser, or YAG laser. YAG lasers produce invisible light in the near-infrared spectrum. The human eye sees only light of shorter wavelengths. YAG lasers are particularly eye hazardous because they focus on the human retina. Looking directly at a laser beam, even from several miles away, can cause severe eye damage. Reflected laser energy is also a hazard. All laser sighting devices have built-in filters to protect the operator. Used properly by trained operators, laser systems are safe and have many advantages over other systems. One advantage is that a laser beam remains narrow and intense over long distances. For example, at 1 mile, the collimated laser beam forms an intense spot less than 30 inches in diameter. By comparison, at this range, a powerful narrow beam flashlight throws a faint circle 1,500 feet in diameter. The invisible laser beam must be aimed. Therefore, pointing accuracy is essential for system effectiveness. Because the beam is extremely narrow and travels long distances, vibration of the laser mount, or user movement, introduces spot jitter, hampering laser performance significantly. Invisible collimated laser light is less susceptible to detection and countermeasures than other active sources. Radar, for example, emits energy in a widely dispersed pattern, which can be quickly detected and readily jammed. Reflected laser energy is also difficult to detect, and if detected, is more likely to reveal the target than the source. Since laser energy is usually released in pulses, security against countermeasures is strengthened by altering the pulse repetition frequency, the PRF, from laser to laser. PRF coding also permits simultaneous attack of different targets in the same combat area. Each target designator has a large number of operator-selectable frequencies. The weapons are programmed to respond only to a specific pre-selected frequency. They disregard all other laser energy and guide only to their intended targets. A ground-based forward observer with a laser target designator can direct laser-guided weapons from aircraft, ships, or ground-based artillery. The laser, however, must have an unobstructed line of sight to the target. If not, every tree, rock, and bush it strikes may look like a target to the incoming ordnance. Additionally, if the laser beam is too wide, or if the target is too small, laser energy spills over the target, illuminating unintended areas, possibly creating false targets. One laser system in development, the Mule, not only designates targets, but determines azimuth, elevation, and true north. This improves significantly the accuracy of conventional ordnance delivery. Airborne laser systems also have grown in accuracy, capacity, and sophistication. The Laser Spot Tracker, LST, developed at the Naval Weapons Center, is an airborne search set that scans target areas and automatically locks on to a target designated by a forward observer. The forward observer aids LST-equipped aircraft in locating obscure targets. The forward observer illuminates a prominent terrain feature which the pilot can find easily. After the aircraft is headed toward this initial point, the observer moves the designator to illuminate the actual target. With the target designated, the aircraft, without changing heading, releases ordnance which guides to the target. The Angle Rate Bombing System, ARBS, is another NWC-designed airborne laser system which uses a ground-based target designator. ARBS contains a laser tracker and a computer to calculate bomb release point. ARBS senses reflected laser energy from the target and calculates the bomb release point based on the aircraft's angle of attack, velocity, and range. Accuracy is much greater than with conventional bombing. Pave Knife is a pod-contained laser target designator system. The laser is bore-sighted to a low light level TV camera used to identify and track targets. The Bombardier navigator lasers the target while observing it on the TV screen. With the target designated, laser-guided weapons are launched from either the Pave Knife aircraft or another aircraft. The Night Observation Surveillance System is a self-contained 24-hour airborne surveillance and target designation system. It consists of a modified OV-10 equipped with a forward-looking infrared or FLIR system and a laser target designator and rangefinder. The FLIR detects infrared radiation emitted from targets, allowing accurate ground target assessment either day or night. The laser designator, aimed with the FLIR, illuminates the target for weapons from the OV-10 or from other aircraft. Another airborne laser system, the Target Recognition Attack Multisensor, TRAM, is a state-of-the-art target sensor and designator for high-performance attack aircraft. TRAM has three key elements: a high-resolution FLIR search set for viewing, target detection, and tracking, a laser for target designation, range finding, and weapon guidance, and a laser receiver to locate targets designated by other lasers. Because all TRAM sensors are contained in a multi-axis turret, targets are tracked continuously. A look-back capability allows tracking, weapon guidance, and bomb damage assessment as the aircraft leaves the target area. Lasers are used also in weapons fusing systems. New generation Sidewinder air-to-air missiles use 4 gallium arsenide lasers in their proximity fuse. Each laser covers about 90 degrees around the missile's axis. Receivers in the fuse sense reflected laser energy from the target and detonate the warhead at a distance of maximum lethality. Laser ranging fuses initiate bomb burst at the optimum height above the surface to achieve maximum effectiveness. Research and development is continuing into laser technology to develop new applications and to improve existing systems. Carbon dioxide lasers, widely used in laboratories, may complement YAG lasers in future low-power field uses. Light from carbon dioxide lasers can be seen by imaging infrared viewers. And the infrared energy from carbon dioxide lasers penetrates smoke, fog, and haze much better than YAG lasers of the same power. Also, carbon dioxide lasers are much less dangerous to the human eye than YAG lasers. Laser data and communication links are being developed. They are secure and extremely directional, with an almost unlimited data handling capacity. The active laser seeker, being developed for air-to-air missile weapon systems, is a search and track system using a high PRF laser and a matched receiver. The system locates the target, locks on, and feeds directional, angular, and closing data to the missile. The active laser seeker has high target selectivity and low countermeasure vulnerability. From laboratory research to advanced fleet systems, lasers are in the forefront of naval technology. Lasers are safe, versatile, precise, and uniquely applicable to our modern fleet systems. Laser use, with its speed and reliability, is an important link in defeating an increasingly sophisticated threat.